Hello everyone, myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to see the problems on statistical independence. So, at the end of this particular session, we will be learning two learning outcomes. Firstly, the first learning outcome is defining the statistical independence of random variables. The second learning outcome is we will apply this concept for solving the practical problems. We will recall what is meant by the statistical independence. We have defined already statistical independence for events. So, if two events are said to be statistically independent, if and only if P of A intersection B is equal to P of A into P of B. So, this is the condition we applied for events. When it comes to random variables, we need to see the condition. The conditions are expressed in terms of two things. One is joint distribution function and joint density function. So, the joint distribution function is the product of individual marginal distribution functions. Then we can say x and y are statistically independent. Otherwise, the joint density function is the product of individual marginal density functions. Then we can say statistically independent. So, when it comes to random variable x, assume A is nothing but x less than or equal to x and B is associated with y, y less than or equal to y. The probability of x less than or equal to x, y less than or equal to y is equal to probability of x less than or equal to x, probability of y less than or equal to y. So, this is nothing but distribution function. This is the marginal distribution function of x, this is marginal distribution function of y. When you apply the derivative, so the derivative of distribution function gives you the density function, derivative of distribution density function. So, like this we can develop the relationship for random variables. So, when it comes to random variables, to verify the statistical independence, we can use either distribution function condition or density function condition. So, we have defined the statistical independent. So, the statistical independence concept let us apply for the practical problems. So, the joint density function is expressed as fxy of xy is equal to k into xy e power minus of x square plus y square, and the x and y limits are mentioned in the problem. We are asked to compute the value of the k, unknown value k, and also we are asked to compute or verify whether the random variables x and y are statistically independent or not. So, firstly, to compute the constant k, we have got the property in the joint density function. So, for any density function to be a valid joint density function, the area under the density function must be unity. So, this is the condition we need to apply to verify the function to be a valid density function. So, by applying this one, so clearly it is given that x is greater than 0, y is greater than 0. So, x limits and y limits are 0 to infinity, k xy e power minus of x square plus y square dx dy. So, what we will do is here, first we will assume this x into e power minus x square dx. First we will see this one partial thing. Assume x square is equal to t, 2x into dx is equal to dt. So, 1 by 2 e power minus t dt, this value is 1 by 2. In a similar manner, both are symmetrical, we will get 1 by 2. So, now k into 1 by 2 into 1 by 2 is equal to 1. The area under this density function is unity. From this, what we will get, k is equal to 4. The unknown constant k is 4. Next, we will, in order to verify the statistical independence condition in terms of density function, so this is the condition that should be satisfied for the random variables to be statistically independent. So, before going to that, we need to compute the marginal density function of x, marginal density function of y. So, the marginal density function of x can be computed using the property. So, if you integrate with respect to y, you will get the marginal density function of x. If you integrate with respect to x, you will get the marginal density function of y. So, the joint density function is written and the valid limits are mentioned here, 4xy e power minus x square plus y square. So, e power a plus b can be written as e power a into e power b. So, since we are integrating with respect to y, I am taking the x limits outside and this integration value already we computed, that value is 1 by 2. So, what we will get 2x into e power minus x square, and the x limit is mentioned here. In a similar manner, since both look symmetrical, fy of y can be computed by integrating with respect to x. What we will get, 2y into e power minus y square, y greater than 0. When you multiply both functions, 2 into 2, 4, x into y, x y, e power minus x square into e power minus y square, e power a plus b, e power minus of x square plus b square. So multiplying that, what we will get, 4xy e power minus of x square plus y square. So LHS is equal to RHS, hence the two random variables x and y are statistically independent. Let us solve one more problem related to the statistical independence. The joint probability density function of a random variable x and y is given, density function is defined and provided the limits. Again the same thing, we need to compute the unknown value k, we need to compute the marginal density functions, and also we need to verify the statistical independence. Along with that, one problem is given, we are asked to compute the probability over the limits x is between 0 to 2 and y is limiting between 2 to 3. So to compute the unknown value k, we have got one property of joint density function. The area under joint density function must be unity. For any function, for any valid density function, the area under density function is unity. We will apply this condition straight away here. X limits are between 0 to infinity, y limits are from 0 to infinity, k into e power minus of x plus y dx dy. So what we will do is, e power a plus b I am writing as e power a into e power b, e power minus y I am separated, e power minus x integration, substituting the limits I will get 1. Similarly, e power minus y integration, substituting limits I will get 1. So totally the k must be equal to 1. So this is unknown value of k is obtained by applying the area under joint density function is unity. Next we will compute the marginal density functions of x and marginal density function of y. So in order to compute the marginal density function of x, again we will use the property of joint density function. When we integrate with respect to y, we will get the marginal density function of x. When you integrate with respect to x, you will get the marginal density function of y. So we will do the same process. So the y limits are from 0 to infinity, e power minus x is a constant I am bringing outside. Integrating e power minus 5 over the limit 0 to infinity, I will get 1. So e power minus x, and it is valid from x greater than 0. Similarly, fy of y, you do the integration with respect to dx. While doing the integration with respect to x, e power minus 5 is a constant I am bringing outside, its value will get 1. And here also y greater than or equal to y greater than 0, x greater than 0 limits. So fx and fy are computed. And the third one is, we are asked to compute the probability over the limit 0 to 2 and 2 to 3. So this also will apply the property. If you want to compute the probability between any two limits, what we need to do is, we need to compute the area under those limits based on the property of joint density function. For computing the area, the limits are y1 to y2, x1 to x2, fxy of xy dx dy. So applying that and computing this, what we will get is 1 minus e power minus 2 into e power minus 2 minus e power minus 3. So this, substituting the e, you will get a numerical value, or else you can express your answer up to this extent. Next, and the fourth problem is, subpart is, we are asked to verify whether they are statistically independent or not. To verify the statistical independence condition, fxy of xy is equal to fx of x into fy of y. So fx of x, already we computed, what we get, e power minus x, fy of y e power minus 5, multiplying both, e power minus of x plus y. So LHS is equal to RHS. So clearly x and y are statistically independent random variables. One more problem related to the statistical independence. Along with that, we need to compute the unknown value of k, and also we need to compute the probability of x greater than y. So in order to compute the value of the k, we have got one property, that valid density function property. We will compute the area and we will make it equal to 1. So, the same thing we are following here. K is unknown value I am bringing outside, e power a plus b I am writing as e power n to e power b, e power minus ax. First we are doing integration with respect to y, e power minus ax is a constant. Integrating this and substituting the limits, what we will get is 1 by b. So, k by b again I am bringing outside, integrating for e power minus ax, again I will get 1 by a. So, totally k by ab is equal to 1. From this, k is equal to ab. Next, to verify the statistical independence, obviously we need to compute the marginal density function of x and marginal density function of y. The marginal density function of x can be computed while doing the integration with respect to y. When you are computing integration with respect to y, x terms I am bringing outside, and this integration leads to 1 by b, b cancels out, a e power minus ax. In a similar manner, we will get b e power minus by, fy of y, symmetrically things. So, multiplying, again the condition is satisfied, both are statistically independent. Now, we got one problem that we need to compute the probability of x greater than y, x greater than y. So, y limits I will keep as it is, y is equal to 0 to infinity. So, to compute anything, what we need to do? We need to do the compute the area over the limits. So, y limit I am taking as it is, x limit I am making sure that, x limit I am keeping as it is, y limit will be x is greater than y. So, y is the upper limit, y is the upper limit. Substituting the limits and calculating, what we will get, b by a plus b. The probability of x greater than y is b by a plus b. Now, we will see one problem which is related to the discrete random variable. So, the earlier problems we have seen are category of continuous random variables. Now, we will see the discrete random variables. The joint probability mass function is given to us, and x limits are for 1 and 2, y limits are 1 and 2. Now, we will see how to compute the value of unknown value of k, marginal probability mass functions, and we need to verify the statistical independence. So, in order to compute the value of k, we have got one property in probability mass function. The sum of all the probabilities of the events defined on the random variables must be equal to 1. So, we have got two random variables, the joint probabilities must be equal to 1. Applying that condition, x limits are from 1 to 2, y limits are from 1 to 2, k into x plus 2y. So, k into, first I substituted the y limits, y, k into x plus 2 and plus x plus 4, this is equal to 1. Next I substituted the x limits, 2x plus 6 is equal to 1. X limits after substituting, what we will get, k into 8 plus 10 is equal to 1. So, the k value is 1 by 18, k value is 1 by 18. You can substitute like this, k into x plus 2, first for y is equal to 1, x plus 2, for y is equal to 2, x plus 4. Next, substituting the x limits, for x1, 1 plus 2, for x2, 2 plus 4. So, like this we can compute 6 into 3, 18. Okay. Next, we need to compute the marginal probability mass functions. So, in order to compute the marginal probability mass functions, what we will do is, so while computing the probability mass function of x, we need to make y as infinity, and while computing the probability mass function with respect to y, x will be made as infinity. So, the functions we will get x plus 3 by 9, 4y plus 3 by 18. When you multiply both them, so fxy of xy should be equal to fx of x into fy of y for statistical independence. So, similar manner, pxy of xy is equal to px of x into py of y. Doing this, both are not equal. So, clearly x and y are dependent on each other, not independent. So these are the things we need to compute. Unknown value of k, marginal probability mass function, and to verify the independent or dependent. So in this session what we have seen is, we have defined what is meant by statistical independence for the random variables. So first we started with events, statistical independence of events. We extended the formula to random variables, and we derived the conditions for distribution function and density function. Based on the conditions, we applied the concepts for solving the practical problems. In the practical problems, when density function is given, distribution function is given, how to verify the statistical independence for random variables we have seen. So in the next session, we will expand this one. Thank you.